Whenever I show this slide, people always tell me, there's no lion in statistics. Anyway, this presentation is based on a talk I gave in Richmond, Virginia back in June at a STAT conference, and I also previewed a little bit of it at Minnowbrook back in October of last year. The purpose of the presentation was to explain regression in a new and unique way, using simple terms, and to provide students and practitioners with software that reflects this new concept. You're a bit of a different audience, so I'm going to talk about regression, but through the lens of marketing and designing an APL application. So, taming regression, specifically, this is a case study in how to market your Dialog APL application. Again, I'm fairly new at this, but I want to explain my experiences. How to make APL syntax user-friendly to non-APL users. Create things that competitors can't do in other languages. Design user functions and operators to be consistent with APL primitives. And also, last but not least, to provide APL programmers with useful source code for other apps. So the conference I went to was sponsored by the American Statistical Association, and it was in Richmond, Virginia, June 4th to 7th. There were over 300 people there. They had about 3 or 4 parallel sessions. About 35 people attended my presentation on taming regression. Some of the comments, someone was talking about least squares regression, and can we also do maximum likelihood, and I'm currently working on some of that. Big question was, when will the web version be out? Students, they don't like to install programs on their computers and everything. They just want to go to the web and do it. We've made some progress on that. I've been working with Michael Bass on getting a web version out, and I'll talk about that a little bit later. Here was one of the comments from one of the attendees at the STAT conference, and I think it speaks for itself. Anyway, he was very pleased, and I talked to him on the phone and everything, and he's a graduate student, he wants to use TAMSTAT in his teaching, because he teaches statistics. So I was very pleased with this email when I got it from him. Okay, my daughter got married about 6 years ago, and so I'd like to say it went off without a hitch, but they got hitched anyway. As father of the bride, I had the enviable task of paying for the wedding. So at that time, it was about $500 to rent the hall and about $100 per guest for food and stuff like that. So this kind of case, so this basically can be represented by a linear function. F of x is fixed cost plus variable costs. But we're going to look at this through using three different perspectives. So we can, first of all, we can write this as a function in APL, and I used it this way for a specific reason. I'm using the jot there. So the first way we're going to look at it is, what is the final cost if you invite 35 guests? What's the final cost? So basically, it's a simple function. Y is equal to f of x, and I'm going to use this color scheme. Y is the unknown, and x is the known value. And we can just apply our function f, and we get out a cost of $4,000. Okay, the second way to look at this is, how many guests can you invite with a budget of $8,000? Well, in this case, what's unknown is x, and what is known is y. And we can use, this is a little bit harder, we have to use algebra. So we're making a progression from arithmetic to algebra, and we can use the inverse function, and we get out the value 75. So we can invite 75, if we have a budget of 8,000, we can invite 75 people. Third perspective. You're in the catering business. How much do you charge for the venue, and how much do you charge per person? Okay, well, this is where regression comes in. And so in this case, we know both y and x, but we don't know f, the function. Okay, so this is a little harder. So in this case, we're going to check sales records from other caterers for total cost and number of guests. And we're going to do regression, and of course in Dialog APL, we can use Domino to do that. And we get out the fixed costs and the variable costs, or the intercept and the slope. And so that's basically how I explain regression to my students. And regression in TAMSTAT is kind of based on this idea. There are some issues. We don't just want the slope and the intercept. We want to actually create the function f. We also, the data are based on a sampling, so we want to put in a confidence or prediction interval around the result. The relationship between x and y may not even be linear, so that could create some other problems. The variance may not be constant over the range of f. We may want to include qualitative variables, categorical variables in our input. If we have multiple inputs, we want to preserve meaningful names. So the question is, how do we do this? So we have an operator that we call regress that's in TAMSTAT. And the regress operator can perform simple linear regression, multiple regression, regression with what we call indicator variables. These are character fields. Polynomial regression. I'm going to show a few of these examples. Variance stabilizing transformations and some other things. And finally, logistic regression and general nonlinear regression. So we can do a lot of these things. I won't have time to show all of them, but I'll show several of them. And if not specified, the operand is assumed to be linear. So if you don't put in an operand, and I do this with a little bit of sleight of hand, but you can leave out the operand. It does linear regression. If you put in an operand, it will do some type of nonlinear regression. So the regress operator produces a namespace, and I'm going to call it model because it's basically, we're creating a model. And the namespace contains a list of several variables. Variable b is basically a vector of coefficients, starting with the intercept and then the slope, and then if you have more than one variable, it's just a list of coefficients. And if you're familiar with statistics and regression, R squared tells you how much variation is due to the regression, the standard error, the predicted or fitted values, residuals, which is the error terms, and an ANOVA table. And most statistical packages do this stuff. They provide this information. But there's one thing that TAMSTAT does that these other packages do not. We actually create a function f. And so that's kind of the big feature, the unique defining thing that we do here. Here's a simple example. We have a car dealer runs TV ads for 5 weeks and records the number of cars sold. And so here's the data. And you want to predict sales from the number of ads run. So this is an example of simple linear regression. Our predictor variable, we just create a vector with all the ads, for 5 weeks of ads. And then the response variable are sales. And now I'm going to take the regress operator, and we take sales as the response and ads as the predictor variable, and we create a model. Okay, it's an operator, so sales, it looks like a function, a dyadic function, but sales is actually the left, is the operand, but to the user it just looks like a function. So if we want we type in model.b, we get the intercept, which is 10, the slope is 5. We can list the equation, and the equation is actually executable in Dialog APL, and thanks to Gitta, she suggested that we make it actually look executable. So it's actually, the parentheses and everything are there. The error term is just the E is an error term that tells you the difference there. So I can now take model.f, which is my function, and apply, instead of just typing in that equation, I can just say model.f, so that equation is actually embedded in model.f, and it will give me, if I run 2 ads, I can sell 20 cars. But we're not done yet. There's more stuff here. What if I want to estimate my mean sales for the next week? This is based on a sample, so if you put in, I may not sell exactly 20 cars, so I'd like to know a range of how many cars I'm going to sell for the next week. So I would apply a confidence interval, and on the average, if I run 2 ads, I should sell between 17 and 23 cars, with 95% confidence. Notice that I did not, 95% is sort of the implied value, so I can supply a left argument if I want to be 99% confident, then I get a wider range. And so I can supply a default left argument there. I can also apply multiple inputs. So basically, this just follows naturally from, I didn't really have to code anything special, but if I put in a vector, I should get out a vector of predicted values. So I just put in a vector. If I want to predict dealer sales for a particular case, I have something called a prediction interval. So it's a different, confident and predint are operators that apply to this function f, which is a user function, which is created by the regression operator. And so now I apply, here if I put in a vector and I create a confidence or prediction interval, I get a matrix, and the rows correspond to the items and the columns, 2 columns for the interval. So again, I'm using APL concepts, but for users that may not really be that familiar with APL. We have 2 regression wizards that we can use, so I want to explain them. We have one called univariate regression, which is fairly new. I've been working on the wizards with Michael Bass here, and here you specifically have one predictor variable. It can either be simple or nonlinear regression, and we created some output graphics, which I'll demonstrate in a little bit. And then the existing multivariate regression, and I won't really have time to demo this one, but this one, you can have 1 or more predictor variables. You can you can do more things with it. The opening slide was an example of that. So when you saw the opening slide with the lion tamer, and there was a graph and stuff like that. Here is an example of the new wizard, univariate wizard, where you just input the significance level, the response variable, transformation. The transformation is new. Here, in this case, it's linear, so there's no transformation. And in this case, I'm taking some data, and the green line in the middle is the linear regression line, and then the confidence bounds are in red, so that and you can see how that line kind of fits the data, and so that's what's going on. The wizard also creates a report. I can't show it on this slide, but the report looks like this, which looks very typical of a regression report that you would get from any other package as well. Multiple regression, and in multiple regression, you have more than one. You have one response variable, you have a bunch of X variables, a bunch of predictor variables, and so you can either use a variable list, a matrix, or a namespace to represent that. we like to give users multiple ways to do that. And the left argument represents the response variable, and the right argument represents the predictor variables. And so here we have, if we want to predict weight from height and shoe size, I have a database of student data that I collected when I teach my classes. And if you generate a report here, you have height and shoe size are two predictor variables. And so you get a report, and it lists the variables as just the coefficients as B1 and B2. So we don't have the names in there. And so we'd like to be able to do that, so we can do this in a different way. We can use a namespace. And so I have a namespace. A database basically is a namespace containing a bunch of variables. Each one is a vector, usually is a vector of values. And so here I'm going to, I want to create a namespace with specifically only the variables that are used in the regression. So here I create a list of names, and then SD is a larger student database, which I have. It has a whole bunch of stuff in it. There's a lot of stuff I don't need. So if I say V select from student data in Tamstat, it will create another database which only has those three variables in it. And now, when I run regression, all I have to do is name which is the response variable. Everything else is a predictor variable. And so I create a model. And now here, height, if a person has, I can apply my model.f, the model I created. A person who's 68 inches tall with a 9.5 shoe size, I predict the weight would be 158 pounds. And I can create a prediction interval if I want. And the nice thing about doing it this way is when you generate the report, you'll notice at the very bottom here, height and shoe size, instead of getting B1 and B2, you get the actual variable names. And so that's the nice thing about using a namespace, because the names you can capture the names of all the variables in it. Another example would be indicator variables. Character fields are treated as indicator variables, and I'm going to kind of skip through this by showing you an example. Basically, an example of indicator variable would be like sex, male and female. And so here we have CSI Scranton. You're investigating a murder. You find a bloody footprint near the body, and it's a man's shoe, size 9.5. So we have two inputs. We know that the perpetrator was male. We know that and we know the shoe size. The question is, what is the height of the suspect? So in order to do this, we have a lineup here. I need three variables: height, sex, and shoe size. Okay. So I select those from my database, and now I want to. Height is my response variable. The other two are my predictor variables. Notice sex is a character field. Okay. So what it does is it's going to create a field called male or female. It's going to create here's the equation. Okay. So the equation here is my intercept is 52.2, but now you notice it's 2.97 times m, which is male. Okay, so it creates a field called male, which has a 1 for male and 0 for female. And then we have the shoe size. And so now if I have a point estimate, 1 represents male, 9.5 represents the shoe size, so the perpetrator is about 68 inches tall. And again, we can put a 90% prediction interval around it. And we can say, well, he's between 5'5" and 6'1". So you have to pick one of those guys that falls in that range. What about nonlinear regression? Here's a scatter plot of some data, hardwood concentration versus tensile strength. And obviously, you can't use linear regression on that because there's a definite curve in there. So we're going to do something called quadratic regression. So I have an operand called quad. And so now I'm going to say model is y, and I'm going to put in the operand quad regress x. So that's quadratic regression. So now when we get our model.b, we're going to get 3 coefficients. And what are they? So the first one is the intercept, the second one is the linear coefficient, and the third one is the squared coefficient. Notice that the squared coefficient is negative. When you have that coefficient negative, that means concave down. So now we're going to apply, now we can't apply model.f because that's a linear function. So when we do quadratic regression, we create another function called model.g. Now, I think most packages, they just create a linear version and then you have to put in the values here. But model.g will take, I'm giving it a vector here, and it actually calculates, it actually has the nonlinear, it just takes one input, but it creates a linear term and a squared term, and it also subtracts off the mean to get rid of collinearity and stuff like that. So you can see here, I'm applying a vector, so you can see that the vector is increasing 7, 10, 15, but the response is going up and then coming back down again, so that is a nonlinear case. And I can also apply a confidence interval to it, and it takes that into account, and a prediction interval. Here's the equation. So you can see that there's an intercept, and then the first term, the linear term, is x minus its mean. The mean is 7.3, and in the second one is x minus 7.3 squared. Again, that gets rid of problems with collinearity, but it's all done automatically. Here are the coefficients and the standard error, t-distribution, if you're familiar with statistics. And if we use our wizard, you can see that we can create a curved model, okay? And so, again, thanks to Michael for helping me get this thing working. You can also do cubic models, and this is called a cubic spline, okay? So you can divide, a cubic spline, you can divide where it says knots at the bottom 7 here. At the point 7, it actually does a spline. It creates 2 cubic models and then connects them with a spline. I know somebody else talked about splines yesterday, the graphics talk and everything, so they come in handy sometimes. Finally, logistic regression. This is a case when your response variable is Boolean. You get just a 1 or a 0. So one example of this is, can you predict a person's sex based on height? So we let y equal sex equals m, so we're just creating a Boolean, and x is height. And logistic regression, one of the problems is you want your response to be between 0 and 1. You can't have it outside that range. And so you have to use this model. It's 1 over 1 plus e to the, to b times your x values. So this is called a logit function or logistic function. And your prediction is you want to predict whether you have a male or a female based on the person's height. And the predicted value is going to be a probability in this case. It's going to be a fraction between 0 and 1. So it represents the probability that y equals 1 or that the person is male. So the slope and intercept must be solved numerically by providing a starting point. So this is a lot more complicated. So we're going to create a guess. Our slope and intercept is 0.2 and 0.001. And so now we're going to do logit regress. The operand is logit. And the intercept and slope, these aren't really as meaningful as they would be in linear regression because this is a nonlinear response. But we can predict by using ml.g, predict if a person is 68 inches tall, what's the probability that person is male? And we get 82%. Okay, so that's how that works. And again, we have a nice, this is a scatter plot of what that looks like. Okay, so how do you download and install Tamstat? Tamstat runs on Windows, and the Mac is free to use and can be downloaded from the following website. So we have a website out there, and there's also a an online version, you can a web version that's out there, and you can get there from that site. So so a web version is also available. So, in conclusion, I said these are the things that I want to talk about. If you want to market your Dialog APL application, what I did was go to conferences where there are domain experts. So I went to a STAT conference. Bring a laptop and demo your software during the refreshment breaks. I made a point of doing that. I brought my laptop and I showed what Tamstat could do. Creates graphics that will wow the customer. You want to have, and so that's why I'm very grateful for Michael for helping me out with the graphics here. Make APL syntax user-friendly to non-APL users. I want to make the functions flexible and use English-like syntax. Okay, and so I made a point of doing that in Tamstat. Create things that competitors can't do in other languages. Okay, so in this case, I used operators. They don't have them in other languages. And I created the F function and the G function dynamically, okay? This is something that really you can't do it except in APL. I don't think there's any way to really do that. Design user functions and operators to be consistent with APL primitives. In that case, what we did was, where appropriate, many defined functions can be made to behave like scalar functions. And so I showed that. You can apply a vector and it does things item by item. Create ambivalent functions which supply default values. So I do that, and I had an example of that. And finally, provide APL programmers with useful source code for other apps. So Tamstat is available on GitHub. It's under Tamstat Core, and so if you want to use Tamstat functions in your application, feel free to go to Tamstat Core and get them. Okay, so that's it. So if anybody has any questions, I will be happy to answer them.